A black hole is a tear in the fabric of reality. These cosmic monsters and their impossible cores, singularities, are the ultimate enigmas of space, challenging everything we think we know about physics. By the end of this journey, you will have explored 30 of their most profound unsolved mysteries, a tour that takes us to the very edge of known science and beyond. We will confront paradoxes where information vanishes forever, question if a blazing firewall guards the entrance, and even ask what, if anything, lies on the other side of the tier. What cosmic mystery makes you question the nature of reality itself? Our first mystery strikes at the very heart of modern physics, a conflict so deep it threatens to unravel our understanding of the universe. This is the information paradox, a puzzle so profound it kept Stephen Hawking awake at night. It begins with a simple, devastating idea. According to Hawking's own groundbreaking work, black holes are not truly black. They slowly leak a faint glow of particles, now called Hawking radiation. Over immense stretches of time, this process causes a black hole to completely evaporate, vanishing from the cosmos. And here lies the catastrophe. Everything that ever fell into that black hole, every atom of a star, every bit of data from a lost civilization, seems to be erased from existence alongside it. That information is gone forever, but quantum mechanics, the rulebook for the very small, states this is impossible. One of its most sacred laws is the principle of unitarity, which says information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. If a book burns, the ash and smoke still contain the information of its words. A black hole's evaporation appears to be the one exception, a cosmic shredder that violates this fundamental quantum law. So we are left with a brutal either-or. Either Hawking radiation is wrong, or quantum mechanics is incomplete. Both theories are pillars of modern science, yet they give us completely contradictory answers about the fate of reality itself. Physicists have proposed some truly mind-bending solutions to escape this paradox. One leading idea is the holographic principle. It suggests that all the information about what fell into the black hole is not lost inside, but is instead perfectly encoded, like a hologram, on the two-dimensional surface of its event horizon. The three-dimensional interior we imagine is just a projection of that data. Another, more violent proposal is the firewall hypothesis. It argues that instead of a smooth, empty space at the event horizon, there exists a searing wall of high-energy particles that instantly incinerates anything crossing it. This firewall would protect the laws of quantum mechanics by preventing information from ever actually entering the black hole in the first place, but it would blatantly violate Einstein's prediction of an uneventful fall. Each solution fixes one theory by breaking another, leaving us in a dizzying loop of cosmic contradictions. The fate of information, and perhaps the consistency of reality itself, hangs in the balance. That paradox forces us to look deeper, to ask what lies at the very center of this cosmic contradiction. The ultimate source of the trouble is the second great mystery, the singularity itself. This is not an object you can touch or see. It is a mathematical prediction, a point of infinite density where the entire mass of the collapsed star is crushed into a volume of zero size. The equations of Einstein's general relativity, which so beautifully describe the warping of spacetime around a black hole, simply blow up at this point. The curvature of spacetime becomes infinite, gravity becomes infinite, and our understanding of physics comes to a screeching, nonsensical halt. It is a place where cause and effect have no meaning, and the very concepts of space and time cease to exist. This tells us one thing with absolute certainty: our theory is incomplete. To solve the riddle of the singularity, we need a new theory that can marry the vast cosmic scales of gravity with the bizarre quantum rules of the subatomic world. We need a theory of quantum gravity. Without it, the singularity remains a glaring sign that says, "Here be dragons." Physicists have proposed some wild alternatives to avoid this mathematical monster. One idea is the gravistar, short for gravitational vacuum star. Imagine if, instead of a crushing singularity, the black hole's core was a bubble of exotic dark energy, a repulsive force so powerful it halts the collapse entirely. The surface of this bubble would look just like an event horizon from the outside, but inside, space-time would be radically different, preventing the formation of that impossible point. An even more mind-bending proposal is the Planck star. In this scenario, the collapse does create a tiny, dense core, but not an infinitely small one. When it reaches the smallest possible size allowed by quantum physics, the Planck length, a tremendous quantum pressure from the very fabric of spacetime kicks in. This pressure causes a cosmic bounce, like a rubber ball hitting the floor. The singularity is avoided, and the core begins to expand again, perhaps even giving birth to a new universe in a colossal, hidden explosion. These are not just flights of fancy, they are serious attempts to erase the infinity from our equations and replace it with something that obeys the rules of a deeper reality. The true nature of the black hole's heart remains the greatest unknown, a blank space on the map where our physics ends and true discovery awaits. This fiery solution to the information paradox creates a terrifying new dilemma. If the holographic principle saves information by storing it on the event horizon, then what happens to an astronaut falling in? According to Einstein's equivalence principle, crossing the event horizon of a large black hole should be an uneventful, even serene experience. You would feel no sudden jolt, no dramatic tear, just the gentle pull of gravity as you pass the point of no return. But if that horizon is a literal firewall, a searing ring of unimaginably high energy particles, then the astronaut's journey ends in a flash of incineration long before reaching the central singularity. This is the firewall paradox, a brutal conflict where saving quantum information seems to require violating the fundamental tenets of general relativity. You cannot have both a smooth spacetime and a quantum firewall. One theory must break. The debate this sparked within the physics community was fierce. Some argued the firewall is a real physical prediction, a necessary boundary that protects the laws of quantum mechanics by preventing information from ever actually entering the black hole. In this view, the astronaut is not vaporized by the firewall, but rather, their information is instantly scrambled and reflected outward as Hawking radiation, never truly crossing the threshold. Others see the firewall as a glaring signal that our reasoning has gone wrong somewhere, a mathematical artifact rather than a physical reality. They search for more subtle quantum effects that could preserve both the astronaut's peaceful fall and the sanctity of information, perhaps through intricate entanglement between particles inside and outside the black hole. The implications are staggering. Either the universe contains regions of space, the event horizons of black holes, that are fundamentally violent and impassable, contradicting a century of gravitational physics, or our understanding of how quantum information behaves in extreme gravity is still profoundly incomplete. This paradox forces us to ask a haunting question about the nature of reality itself. Is the universe ultimately consistent? Or are there places where its own laws turn inward and create impossible, destructive contradictions? The firewall paradox forces us to confront the brutal physics of the boundary. But what if you could somehow survive the crossing? Our journey does not end at the event horizon. The fourth great mystery asks what, if anything, lies within the dark heart of a black hole. We have spoken of the crushing singularity, but mathematics paints a far stranger and more complex picture for a black hole that spins. Most black holes likely rotate, and for these cosmic whirlpools, described by the Kerr solution, the interior structure becomes a labyrinth of bizarre possibilities. Instead of a single point of infinite density, the equations reveal a ring singularity, a loop of unimaginable density where the known laws of physics still break, but in a different shape. More intriguingly, a spinning black hole's interior is predicted to contain not one, but multiple boundaries. Past the outer event horizon, you might encounter an inner horizon, often called the Cauchy horizon. This is theorized to be a place where the roles of space and time switch again, and where, mathematically, you could see the entire future history of the universe flash before you. It becomes a gateway to potential pathways. Some solutions suggest that the ring singularity could act as a portal, a tunnel through space-time known as a wormhole, potentially connecting to another black hole in a distant region of the cosmos, or even to a completely different universe. Imagine falling through such a tunnel, not into crushing oblivion, but into a new realm of stars and galaxies, a cosmic rebirth from the ultimate collapse. Yet this breathtaking vision comes with a severe warning: the instability problem. Most physicists believe that the inner Cauchy horizon is not a stable gateway, but a region of infinite energy buildup. Any matter or radiation falling into the black hole, along with the light from the entire future, would be focused and blue shifted into an apocalyptic wall of energy at this boundary. In practical terms, the elegant mathematical tunnel would likely be destroyed by its own physics, collapsing into chaos long before any traveler could use it. So we are left with a haunting duality. The pure mathematics of Einstein's equations opens a door to wonders, suggesting universes within black holes and bridges across the cosmos. But the messy, real-world physics of energy and instability seems to slam that door shut. This leaves the true nature of the black hole interior suspended between magnificent speculation and violent reality, a hidden architecture we may never be able to map. The architecture within a black hole remains a theoretical labyrinth, but out in the observable cosmos, these objects present a different kind of puzzle, one of impossible scale and timing. Scattered at the hearts of nearly every large galaxy, including our own Milky Way, are supermassive black holes. These are not the remnants of dead stars. They are cosmic sovereigns with masses millions or even billions of times that of our Sun. Their existence alone is staggering, but the real mystery is how they got so big so fast. Astronomers peering back to the universe's infancy, just a few 100 million years after the Big Bang, have found the brilliant beacons of quasars. These are galaxies with supermassive black holes at their centers, feeding voraciously and glowing with the light of 1 trillion stars. The problem is, there simply wasn't enough time for them to grow that large through the normal process of a star collapsing, and then slowly eating gas and stars. It is like finding a fully grown ancient redwood tree in a forest that was only just planted. So how did these cosmic giants form? The leading theories propose 3 very different origin stories. The first is the idea of direct collapse. In the early, dense universe, vast clouds of pristine gas, unpolluted by heavier elements, may have collapsed under their own gravity not into a cluster of stars, but directly into a massive black hole seed, perhaps tens of thousands of solar masses from the very beginning. This skip-the-star method provides a huge head start. The second theory suggests these giants grew from smaller seeds, the stellar mass black holes left by the first generation of massive stars. But for these seeds to balloon to supermassive size so quickly, they would have needed to feed at a frenzied, nearly maximum rate for their entire existence, a process that is difficult to sustain without blowing away the very gas they need to consume. The third and most exotic idea points to a birth even earlier than the first stars. These could be primordial black holes, created not from dying stars, but from the intense density fluctuations in the first moments after the Big Bang itself. If some of these primordial holes were large enough, they could have served as the perfect seeds, sitting at the centers of emerging galaxies, ready to feast from day one. Each theory has its challenges, and the truth may involve a combination. The existence of those impossibly early, impossibly bright quasars is a beacon from the dawn of time, a direct challenge to our models of cosmic evolution, forcing us to question what monstrous processes could forge such powerful engines in the universe's first fleeting moments. The supermassive black holes at the center of galaxies are hidden behind their event horizons, a protective veil that shields the universe from the infinite weirdness within. But what if that veil could be torn away? This brings us to our sixth great mystery, the terrifying possibility of naked singularities. According to the cosmic censorship hypothesis proposed by the physicist Roger Penrose, nature abhors a naked singularity. The idea is that every singularity, that point of infinite density, must always be hidden behind an event horizon, a one-way curtain that prevents its chaotic influence from leaking out into the wider cosmos. This is not just a neat idea, it is a proposed law of physics, a cosmic rule that ensures the universe remains predictable and causal, because if a singularity were ever exposed, all bets are off. An event horizon acts as a containment field for the breakdown of physics. It localizes the insanity. But imagine a scenario where a black hole spins so incredibly fast that the centrifugal force overwhelms its own gravity, causing the event horizon to shrink, pinch off, and vanish entirely. What remains is a naked singularity, a knot of infinite density floating freely in space for all the universe to see. Without the horizon to contain it, the bizarre, lawless physics at the singularity would be able to influence the outside world directly. The consequences are mind-bending and deeply unsettling. Causality, the principle that cause must always precede effect, could shatter. An exposed singularity could theoretically create closed time-like curves, pathways that loop back on themselves in time. This could allow for time travel paradoxes, where an event could become its own cause, creating logical impossibilities that unravel the consistent flow of reality. The predictive power of our equations would completely fail, as the future would no longer be determined solely by the past. It would be a puncture in the rational fabric of the cosmos. So does nature enforce cosmic censorship? We simply do not know. Some mathematical models of collapsing stars or wildly spinning black holes suggest naked singularities could form under very specific, extreme conditions. Yet many physicists hold a deep intuition that some unknown physical process, perhaps a quantum gravitational effect, will always step in at the last moment to prevent the horizon from disappearing, like a cosmic safety mechanism. The search for a naked singularity is, in a way, a search for a limit to the universe's own sanity. Finding one would be the ultimate scientific revolution, revealing a realm where the rules we rely on simply do not apply, and forcing us to rewrite our understanding of reality from its very core. It is the difference between a monster safely locked in a dungeon and that same monster unleashed upon the world. The terrifying possibility of a naked singularity reveals a cosmos where physics could break free of its cage. But for the matter that actually falls into a black hole, the journey is a confrontation with two equally bizarre and contradictory fates. This is the seventh great mystery, the ultimate question of what happens to anything that crosses the line. From the perspective of the unfortunate astronaut making the plunge, the story is one of violent and inevitable destruction. As they approach the black hole, the difference in gravitational pull between their head and feet becomes unimaginably strong. This tidal force stretches them into a long, thin strand of atoms, a process physicists grimly call spaghettification. For a stellar mass black hole, this shredding occurs well outside the event horizon, a brutal death before the true journey even begins. For a supermassive black hole, with its more gentle gradient, the astronaut might cross the horizon intact, only to be stretched and torn apart deeper within. In either scenario, all the complex structure of their body and ship is utterly erased, reduced to a stream of elementary particles racing toward the central singularity to be crushed out of existence. That is the story from the inside, but from the perspective of an observer watching from a safe distance with a powerful telescope, something utterly different and equally true unfolds. Due to the extreme gravitational time dilation predicted by Einstein, the clocks of the falling astronaut appear to tick slower and slower as they approach the event horizon. From the outside, the astronaut never actually seems to cross the threshold. They appear to freeze in place, fading to red and then vanishing from view as their light becomes infinitely redshifted. It is as if a cosmic snapshot is taken, preserving the last moment of their approach for all eternity. So which story is real? Is the astronaut instantly destroyed, or are they frozen in time forever? The baffling answer, according to relativity, is that both perspectives are equally valid. There is no single universal now. What happens depends entirely on who is doing the observing. This is not a trick of perception. It is a fundamental feature of our universe. The matter both is destroyed inside the black hole and is eternally preserved on its surface from different points of view. This forces us to confront a profound philosophical question about the nature of reality itself. If two observers can witness two completely different, mutually exclusive fates for the same object, what does that say about the concept of a definite objective event? The fate of falling matter suggests that at the boundaries of extreme physics, reality may not be a single, fixed history, but a tapestry of possibilities woven together by the perspective of the observer. The black hole does not just consume matter, it consumes our most basic assumptions about how the universe tells its story. This strange duality of perspective, where matter is both destroyed and preserved, forces us to question what a black hole truly is. If it can hold information in two places at once, how does it store the immense complexity of everything it swallows? The answer leads us to one of the most revolutionary ideas in modern physics, the concept of black hole entropy. Entropy, in simple terms, is a measure of disorder or hidden information in a system. A tidy room has low entropy, a messy one has high entropy. In the 1970s, physicist Jacob Bekenstein made a startling proposal. A black hole must have entropy, and a tremendous amount of it. This was radical because entropy is a thermodynamic property, and black holes were thought to be purely gravitational. simple objects defined only by their mass, spin, and charge. How could a cosmic vacuum cleaner have disorder? Stephen Hawking initially resisted the idea, but his own work on radiation proved Bekenstein correct. Together, they derive the Bekenstein-Hawking entropy formula. It states that the entropy of a black hole is proportional to the area of its event horizon, not to the volume of space inside it. This is a profound shift in thinking. For any normal object, like a book or a star, the amount of information it contains scales with its three-dimensional volume. But for a black hole, all the information about every star, planet, or atom it has ever consumed is somehow smeared across its two-dimensional surface. It is as if the entire three-dimensional interior is an illusion, and the true reality is painted on the spherical shell of the horizon. This is the heart of the holographic principle. Think of the security hologram on a credit card. It is a flat, plastic surface, but when light hits it just right, it projects a three-dimensional image that appears to have depth and solidity. The holographic principle suggests our universe might work in a similar, mind-bending way. The three-dimensional space we live in, with all its galaxies, stars, and people, could be a magnificent projection from a two-dimensional surface of information at the cosmic horizon. A black hole, then, is not the exception to this rule. It is the ultimate, perfect example. It is a cosmic object where the holographic encoding is so efficient and complete that the surface literally becomes the storage device for everything within. This means the maximum amount of information that can fit inside any region of space is not determined by its volume, but by the area of its boundary. It is a limit on reality itself. So the next time you look up at the three-dimensional night sky, consider a staggering possibility. You, the stars, and the vast emptiness between them might all be a grand holographic movie, played out on a distant, two-dimensional screen we can never see. The black hole is our Rosetta Stone, whispering that the universe's deepest truths are written not in the space we occupy, but on the surfaces that contain it. That holographic screen of information paints a picture of incredible density, but to truly test the limits of matter, we must watch it be torn apart. The universe provided just such a brutal experiment with event GW2115. Detected by the LIGO and Virgo observatories in January 2020, this was the clear, thunderous signal of a black hole colliding with a neutron star. For the first time, we witnessed the final moments of a cosmic dance between the two most extreme objects in existence: the black hole, an insatiable gravitational pit, and the neutron star, a city-sized orb of pure nuclear matter so dense a single teaspoon would weigh as much as a mountain. Their collision rippled spacetime itself, sending a whisper of gravitational waves across 1 billion light-years to our detectors. But the signal ended abruptly. The neutron star, it seems, was simply swallowed whole. It did not shatter brightly in a final flash of light our telescopes could see. It just vanished. And that silent disappearance is the source of our ninth great mystery. What exactly happens in that final, cataclysmic merger? The fate of the neutron star depends on a delicate balance of forces. If the black hole is significantly more massive, it simply engulfs its companion in one gulp, like a whale swallowing a minnow. The neutron star passes the event horizon intact, plunging into darkness without a trace. But if the two are more closely matched in size, something far more spectacular and puzzling may occur. The black hole's immense gravity could stretch and shred the neutron star just before consuming it, pulling it into a long, thin stream of ultra-dense matter. In this brief, hellish instant, densities and temperatures exceed anything we can create in any laboratory on Earth, or even in the core of a supernova. It is a window into the most extreme states of matter possible. Physicists desperately want to know what matter becomes under such conditions. Does it simply crush into the black hole singularity? Or could it, for a fleeting moment, transform into something even stranger than a neutron star? One hypothetical object is the quark star. A neutron star is thought to be made of neutrons packed shoulder to shoulder. But under the unimaginable pressure of a merger, those neutrons themselves might break down into their constituent parts, a soup of free quarks and gluons. This quark-gluon plasma is a state of matter that existed only in the first microseconds after the Big Bang. A quark star would be this soup, stabilized by gravity, an entirely new class of cosmic object. Another possibility is the hypermassive neutron star. This is a temporary, unstable beast. For a few milliseconds after the collision, the merged object might resist complete collapse, spinning so furiously that centrifugal force holds it up against its own weight. It would be a neutron star on steroids, but its fate is sealed. It will either slow down and collapse into a black hole, or it might explode in an enormous blast of gamma rays and neutrinos. The silent darkness of GW 2115 suggests a clean swallow, but other, future signals might hold different clues: a flicker of light alongside the gravitational rumble, or a specific pattern in the waves right at the moment of merger. Each collision is a unique experiment, a chance to probe the laws of physics at densities where our textbooks are blank. By listening to the echoes of these cosmic crashes, we are not just cataloging violent events, we are conducting fundamental research into the very fabric of matter, asking what the universe allows to exist when it pushes itself to the absolute edge. These silent mergers reveal the finality of a black hole's appetite, but for many of these cosmic giants, their feeding is anything but quiet. From the poles of some supermassive black holes, nature unleashes its most spectacular and violent fireworks, relativistic jets. These are not gentle streams. They are searing, focused beams of plasma traveling at nearly the speed of light, punching through intergalactic space for distances that dwarf their home galaxies. One jet from the galaxy M87, famously imaged by the Event Horizon Telescope, stretches for 5,000 light-years, a cosmic blowtorch visible across the universe. The raw power is staggering, converting the gravitational energy of infalling matter into a directed eruption that can outshine every star in its galaxy combined. Yet for all their glory, the exact mechanism that creates these jets remains one of astrophysics' most vexing puzzles. How does a black hole, an object defined by its ability to trap everything, including light, become the universe's most powerful particle accelerator? The leading suspect is a dizzying cosmic dynamo. It begins with the accretion disk, a swirling, superheated maelstrom of gas and dust spiraling toward the event horizon. As this material orbits at tremendous speeds, its charged particles generate immensely powerful magnetic fields. These fields become twisted and wound up by the black hole's ferocious spin, like a rubber band being coiled tighter and tighter. At the poles, where the magnetic field lines are funneled into a narrow column, this pent-up energy finds its escape valve. The theory suggests that some of the infalling material, instead of crossing the event horizon, gets caught in these magnetic field lines and is violently flung outward along the poles. It is a cosmic slingshot, using the black hole's own rotational energy to launch a focused jet. But the details are maddeningly complex. How is the jet collimated, or kept so tightly focused over such vast distances, rather than fanning out into a useless cloud. Magnetic fields likely act like an invisible nozzle, pinching and guiding the plasma. The black hole's spin is almost certainly the ultimate battery, but we do not fully understand how that rotational energy is so efficiently transferred to the jet. Some models suggest the key is the ergosphere, that region just outside the event horizon where spacetime itself is dragged around the spinning black hole. Material here could be whipped to incredible speeds, stealing energy from the black hole's rotation before being ejected. Observing these jets is like watching the exhaust of a cosmic engine whose internal workings are hidden behind a shroud. Each new image, from radio telescopes capturing their vast structure to the Event Horizon Telescope resolving their launch point, provides another clue. Solving the jet mystery is not just about understanding a spectacular light show. It is about deciphering how black holes, these ultimate consumers, also become the most influential architects in the cosmos, shaping the evolution of galaxies and seeding intergalactic space with energy and matter across billions of years. Those jets are the black hole's roar, but in the end, even the mightiest cosmic giant faces a silent, cold demise. This is the fate written by Hawking radiation, the slow leak that dooms every black hole to eventual evaporation. For most of its unimaginably long life, this process is a faint whisper, but the final stage is a crescendo of unknown physics, a mystery that takes us to the very edge of what our science can describe. As the black hole loses mass through Hawking radiation, it shrinks, and as it shrinks, it gets hotter. This creates a runaway feedback loop. The smaller it gets, the faster it radiates, growing hotter and brighter in a terrifyingly accelerating death spiral. In its last fractions of a second, a black hole with the mass of a mountain would be radiating with the power of billions of nuclear bombs, a flash of radiation that would outshine galaxies. But what happens at the very end, when the black hole shrinks to the smallest possible size allowed by physics, the Planck length? At this scale, the smooth spacetime of general relativity is meaningless. Quantum fluctuations should be frothing and churning, and a theory of quantum gravity we do not yet possess would take over completely. Our equations simply stop. So we are left to speculate on several profound possibilities for this ultimate phase. The first is pure explosive disappearance. The black hole could radiate away its final bit of mass and simply wink out of existence in a final, brilliant flash of high-energy particles. Poof, gone. But this clean ending brings us right back to the information paradox, where all that data it ever swallowed seems to vanish forever, violating quantum law. To avoid this, physicists propose a second possibility, the stable remnant. Imagine the evaporation stops at the Planck scale, leaving behind a tiny, indestructible nugget of spacetime, a fossil of infinite density but no event horizon. This remnant, smaller than an atom but heavier than a mountain, would be a permanent tombstone, holding the information of everything the black hole consumed for all eternity. It solves the information problem by locking the data away forever, but it creates another, perhaps weirder, issue. The universe could become littered with these invisible, impossible-to-destroy relics, a cosmic graveyard of infinite density. The third and most staggering speculation is that a dying black hole could give birth to a new universe. In this scenario, the extreme conditions in the final moments trigger a quantum bounce, a reversal of the collapse. The singularity does not vanish, but instead becomes the seed for a new Big Bang, expanding outward into its own separate spacetime bubble, disconnected from our own. In this view, our entire cosmos could itself be the interior of a black hole existing in a parent universe, part of an endless, fractal chain of cosmic reproduction. Each of these endings is a different answer to the deepest questions about reality. Does information live forever? Can something come from true nothingness? Is our universe alone? The final flash of a dying black hole is not just an end, it is a doorway, and on the other side lies the answer to what laws truly govern existence at its absolute foundation. The final flash of a dying black hole hints at a universe born from a singularity. But what if some singularities are not ends, but beginnings of a different kind? This leads us to a tantalizing possibility that has fueled science fiction for generations. The idea that black holes could be secret tunnels through spacetime, known as wormholes. The connection is not pure fantasy, it is written in the mathematics of Einstein's own equations. In 1935, Albert Einstein and his colleague Nathan Rosen published a paper exploring the implications of general relativity for the structure of particles. Within their complex calculations, they discovered a surprising solution, a bridge connecting two separate points in spacetime. This structure, now called an Einstein-Rosen bridge, mathematically describes a tunnel with two mouths, each resembling the spacetime curvature of a black hole. In the pure, idealized world of these equations, a black hole's singularity could theoretically be bypassed, connecting to a white hole, a theoretical region where matter and energy are expelled, in another part of the cosmos. This is the origin of the iconic idea, a black hole as one end of a cosmic shortcut. However, physicists quickly realized a brutal reality check. The standard black holes we observe and theorize about are almost certainly not traversable wormholes you could fly through. The Einstein-Rosen bridge in that simple form is unstable. It would pinch off and collapse faster than even a beam of light could traverse it, crushing any hopeful traveler. The tunnel slams shut the instant it opens. To create a stable, traversable wormhole, you would need a miraculous kind of material to line the tunnel and prop it open against the relentless force of gravity. This is what physicists call exotic matter, not just strange matter, but matter with a truly bizarre property, negative energy density. Think of gravity as always pulling, always attractive. To hold a wormhole throat open against this pull, you would need something that exerts a kind of anti-gravity, a repulsive pressure. Exotic matter would have negative mass, meaning it would fall up, not down. It would push spacetime apart rather than pulling it together. While quantum mechanics allows for tiny amounts of negative energy in specific circumstances, like the Casimir effect, the amounts needed to stabilize a macroscopic wormhole are astronomical and almost certainly impossible. Without it, the wormhole is a mathematical mirage. Yet, if such a tunnel could exist and be kept open, the implications spiral into the realm of the unbelievable. A traversable wormhole would not just be a shortcut through space. It would be a machine for time travel. According to relativity, if you could move one mouth of the wormhole relative to the other, say by taking it on a high-speed journey near the speed of light, time would pass differently for each end. When you brought them back together, you could have a situation where walking into one mouth would send you not just to another location, but to another time. This immediately creates the potential for infamous paradoxes, like the grandfather paradox, where you could go back in time and prevent your own birth. The very possibility of such consistent time loops forces physicists to question whether the laws of nature have a hidden mechanism, some principle of chronology protection, that simply forbids them to prevent the universe from unraveling its own history. So while the black holes we see are almost certainly deadly dead ends, Their mathematics whispers of a deeper, hidden architecture. They are a signpost pointing to a profound question. Does the fabric of spacetime allow for these incredible stitches, these shortcuts that weave the cosmos into a connected whole? Or is the universe fundamentally designed to keep its regions separate, ensuring that every journey, no matter how long, must be taken the long way around? The wormhole's promise of connection is a cosmic dead end, but another idea offers an even more radical escape for lost information. When matter vanishes into a black hole, its data might not be destroyed or stored on the horizon. It could be taking a one-way trip to an entirely new reality. This is the baby universe hypothesis, a breathtaking solution to the information paradox that reimagines the black hole not as a tomb, but as a cosmic womb. The concept begins with the singularity. Our current physics screams that it is a place of infinite density where laws break down. But what if that breakdown is not an end, but a transformation? Some theories of quantum gravity suggest that at the moment a black hole forms, or perhaps deep within its heart, the extreme conditions could cause a bubble of spacetime to pinch off from our own. This bubble, inflated by unimaginable energies, would expand under its own rules, creating a separate, self-contained cosmos, a baby universe. Crucially, this new universe would be causally disconnected from ours. No signal, no light, no matter could ever travel back from it. It branches off like a new limb on an infinite tree, forever out of reach. So what falls into the black hole does not get crushed into nothingness. Instead, all the information, every scrambled atom and bit of data, is transferred wholesale into this newborn realm. From our perspective in the parent universe, the information is indeed gone, vanished past the event horizon, never to return. This neatly preserves the laws of thermodynamics from our point of view. But from a God's eye view of the multiverse, the information is perfectly safe, just relocated to another address in the cosmic network. The implications of this idea are staggering. First, it suggests that every black hole could be a creator. Our universe, with its hundreds of billions of galaxies, each harboring a supermassive black hole, might be a prolific factory for new realities, each with its own potentially different physical constants and dimensions. We could be living in a fecund multiverse, a frothing sea of universes being born from the collapse of stars in their predecessors. Second, and more personally, it offers a bizarre form of immortality. If you were to fall into a black hole, your story would not end. According to this hypothesis, your consciousness, your memories, the very pattern of your atoms, would be reborn in the Big Bang of a new cosmos. You would not experience crossing a singularity, because in that moment, you would become the universe itself, its entire history unfolding from your point of view. Of course, this remains wildly speculative, a thought experiment grounded more in mathematics than observable evidence. The greatest criticism is also its defining feature. It is utterly untestable. A baby universe is, by definition, beyond any possible observation or measurement from our own. It solves the paradox by moving the problem to a place where we can never check the answer. Yet, as a concept, it forces us to confront the ultimate meaning of existence. Are black holes the ultimate recyclers, not of matter, but of reality? Is our own majestic cosmos, with all its galaxies and life, merely the interior of a black hole in some grander ancestral universe? The baby universe hypothesis does not just offer a way out of a physics paradox. It suggests that creation and destruction might be two sides of the same coin, and that death on a cosmic scale could be the only true birth there is. That cosmic recycling through baby universes is a breathtaking idea, but it leaves a troubling question hanging in our own reality. If information simply flees to another realm, how can we ever prove it was conserved here? This brings us to a direct challenge against one of the most famous sayings in theoretical physics, the notion that black holes have no hair. The classic no-hair theorem states that a black hole, once formed, is the simplest object in the universe. All the complex, messy details of the matter that created it, the type of star, the planets it swallowed, the composition of a spaceship, are irrevocably lost. The black hole settles into a state described by just three numbers: its mass, its electric charge, and its spin. That is it. Everything else is shaved away, hence no hair. This elegant simplicity is what makes the information paradox so acute. If a black hole is defined only by those three values, then the specific information about what fell in is truly erased, gone without a trace. For decades, this was the accepted, if unsettling, wisdom. But what if the theorem is wrong? A new and exciting idea called the quantum hair conjecture is fighting back. It proposes that black holes might, in fact, have very subtle hair after all, not in the classical sense of bumps or ridges, but in the quantum realm. The conjecture suggests that as matter collapses into a black hole, it could imprint faint but permanent quantum information onto the gravitational field surrounding the hole. Think of it like a watermark pressed into the fabric of spacetime itself. This watermark would be woven from the complex quantum fields of the original matter, perhaps the specific arrangement of electrons and quarks in a fallen star. It would not change the black hole's overall mass, charge, or spin in any measurable classical way, but it would add a unique quantum signature, a fingerprint etched in gravity. This quantum hair would be a way for the black hole to remember what it ate without violating the classical no-hair theorem. The information is not stored inside the hole, nor is it plastered on the horizon. Instead, it is encoded in the very way the black hole's gravity interacts with the universe. Researchers are exploring ways this might be tested, perhaps by studying the gravitational waves emitted when two black holes merge. The faintest ripples in the signal, the echoes of their final orbits, might carry the imprint of their quantum hair, a subtle whisper of their lost history. If detected, it would be a monumental discovery, proving that information is not lost, and that black holes are not the simple, bald vacuums we thought, but complex quantum objects wearing a crown of invisible, intricate data. The universe's ultimate simplifiers might just turn out to be its most sophisticated archivists. Quantum hair hints at a hidden memory etched in gravity, but for a star facing its own death, the final moments are governed by a brutal and precise cosmic rulebook. This brings us to a foundational mystery, the exact line between a stellar corpse and a true black hole, a boundary defined by the Chandrasekhar limit. For a dying star, this limit is the ultimate verdict. Named for the astrophysicist Subrahmanyan Chandrasekhar, it is the maximum mass a white dwarf star can support against its own gravity. Calculate it precisely, and you get about 1.4 times the mass of our Sun. If a white dwarf, say by siphoning gas from a companion star, tips over this limit, it has no future. Electron pressure, the quantum force that holds it up, catastrophically fails. The core collapses in a fraction of a second, but this classic limit is just the opening act for the black hole mystery. For a star massive enough to dream of becoming a black hole, the journey is far more violent and uncertain. The star's iron core, the ash of its nuclear fusion, grows until it too surpasses its own version of the Chandrasekhar limit. At this instant, the core's fate is sealed. but how it crosses the finish line into a black hole is one of the most complex and chaotic puzzles in astrophysics. The process unfolds in the heart of a titanic supernova explosion. As the core collapses, protons and electrons are crushed together to form neutrons and ghostly particles called neutrinos. For a moment, a newborn neutron star is born, its immense density halting the collapse. But whether that halt is permanent or just a brief pause depends on a ferocious tug of war. On one side is the outward rush of energy, carried by a shock wave and a flood of neutrinos so vast, it outshines the entire galaxy. This blast wave must rip through the still falling outer layers of the star to create the supernova we see. On the other side is the relentless pull of gravity on the material just outside the new neutron star. If the shock wave stalls, if it loses too much energy, a terrible thing happens. Material that initially exploded outward falls back, raining down onto the fragile neutron star with enormous force. This is the fallback process, and it can be the final, decisive blow. If enough heavy material, like silicon and iron, falls back onto the neutron star, it can push that core over its own mass limit, perhaps 2 to 3 solar masses. When that happens, the neutron star's own quantum pressure gives way. There is no force left in the universe to stop it. The core collapses past the point of a neutron star, past any known form of matter, and crosses the threshold into a black hole. The uncertainties in modeling this are immense. The explosion is asymmetrical, messy, and governed by poorly understood physics of neutrinos and extreme magnetism. A slight difference in the rotation of the star, or the amount of fallback, can mean the difference between a brilliant supernova leaving a spinning neutron star pulsar and a slightly dimmer explosion where the light is swallowed as a black hole silently forms at the center. So the precise critical threshold is not a single, clean number. It is a chaotic frontier where the fate of a star's core is decided in a maelstrom of failing shock waves, ghostly particles, and gravitational rain. We are left watching the brilliant flashes of supernova, knowing that within some of those cosmic fireworks, a darkness is being born from the precise, violent physics of a limit crossed. But the collapse of a single star is just one way a black hole can be born. There is another, far more ancient and elusive origin story, one that could solve the greatest cosmic mystery of our time. The dark matter that holds galaxies together and weaves the large-scale structure of the universe is invisible, unknown, and everywhere. For decades, physicists have searched for a new fundamental particle to explain it. But what if the answer is not a particle at all? What if dark matter is made of black holes? This is the compelling, controversial hypothesis of primordial black holes. Unlike the stellar mass black holes forged in supernova, primordial black holes would have been created in the first chaotic second after the Big Bang. In that unimaginably dense and hot soup of the infant universe, random fluctuations in density could have been so extreme that pockets of space simply pinched off under their own gravity, collapsing directly into black holes of almost any size. They would be cosmic fossils from the very dawn of time, and if enough of them formed, they could account for all the dark matter we infer from its gravitational pull. The idea is elegant because it uses a known object, a black hole, to explain an unknown force. These ancient holes would be scattered throughout the dark halos of galaxies, including our own Milky Way, their collective gravity providing the invisible scaffold that keeps stars from flying apart. But finding them is a monumental challenge. A primordial black hole with the mass of a planet would be smaller than an apple, and one with the mass of a star could be just a few miles across, drifting through the vast darkness. They emit no light, and if they are not actively feeding, they are nearly undetectable. Our best hope lies in a phenomenon called gravitational microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act as a lens, bending and focusing the star's light. For a brief period, the star will appear to brighten, then fade, in a characteristic curve. Astronomers have been scanning the skies for these telltale flashes for years, using projects like the optical gravitational lensing experiment. The results are tantalizing but inconclusive. We have seen microlensing events, but they could be caused by other faint, ordinary objects like free-floating planets or dim stars. To pin the blame on a primordial black hole, we need more data, perhaps from the precise astrometry of missions like the Gaia spacecraft, which could detect the tiny wobble a passing black hole's gravity would induce in a star's position. The implications are staggering. If a primordial black hole, even a small one, were to drift through our solar system, we might never see it coming. It would be a pitch-black speck of infinite density. Its gravitational influence could subtly perturb the orbits of comets in the distant Oort cloud, sending a shower of icy bodies toward the inner planets. It could even pass through a planet like Earth with almost no effect. Because it is so incredibly small and dense, it would punch a needle-like hole through rock and magma, exiting the other side and leaving only a microscopic tunnel of superheated rock as evidence. The idea that such an ancient, invisible wanderer could be threading its way through our cosmic neighborhood right now is a haunting thought. It transforms dark matter from an abstract concept into a population of real, physical objects with a profound history, relics of creation itself that have been silently shaping the cosmos for 13.8 billion years. The silent, ancient wanderers of dark matter could be anywhere, but in April 2019, humanity pointed its collective eye at a specific, monstrous target 55 million light-years away. We took a picture, the first ever image of a black hole, or more precisely, its shadow, captured by the Event Horizon Telescope collaboration, was not just a technological triumph. That haunting, fiery donut of light surrounding a central darkness is a Rosetta Stone for decoding spacetime itself. The shadow is not the event horizon. It is something larger, a silhouette cast against the backdrop of superheated gas swirling in the accretion disk. The light from behind the black hole is bent so severely by gravity that it wraps around, creating that iconic ring. But the precise shape and asymmetry of that shadow holds secrets. A perfect, non-spinning black hole would cast a nearly circular shadow, but the one we saw, the supermassive black hole in galaxy M87, showed a distinct lopsidedness, a brighter southern rim. This asymmetry is the fingerprint of ferocious spin. The material on the side spinning toward us is Doppler-boosted, blazing brighter, telling us the black hole is rotating clockwise from our viewpoint. By measuring the shadow size and distortion, scientists could estimate not only the black hole's colossal mass, 6.5 billion times that of our Sun, but also the dizzying speed of its spin. Yet the image raises as many questions as it answers. The ring's size perfectly matched the predictions of general relativity for a black hole of that mass. Einstein's theory passed a monumental test in the most extreme environment imaginable. But what if future images, with even sharper resolution, reveal a subtle deviation? The shadow's edge is a laboratory for alternative theories of gravity. Some proposals, like string theory or certain models of quantum gravity, predict that the shadow could be slightly larger or smaller, or its edge less sharp than Einstein's equations demand. Detecting such a flaw in the ring would be like finding a crack in the foundation of modern physics, a sign that gravity behaves differently when space is curved to its absolute limit. Furthermore, the shimmering, turbulent structure within the ring of light is a mystery. The image is a snapshot, but this plasma is dynamic, changing from hour to hour. Future movies of this shadow, compiled from multiple observations, will show how the chaotic maelstrom dances and evolves. This could reveal how magnetic fields thread through the disk and launch those immense relativistic jets, and how energy is extracted from the black hole's spin. That dark central void, the shadow, is a window into a place where space and time are tied into knots. Every photon that reaches our telescopes has skated along the very edge of oblivion, its path twisted by gravity into a final, luminous testimony. The image confirms a century-old prediction, but in its imperfect, glowing circle, we see the outline of our own ignorance, a cosmic cipher waiting for the next generation of telescopes to decode. If the shadow of a black hole is a cosmic sinkhole for light and matter, then its theoretical opposite would be a cosmic fountain, erupting with energy that nothing can enter. This is the white hole hypothesis, a bizarre mirror image of the black hole that exists more firmly in the mathematics of relativity than in any confirmed corner of our universe. In essence, a white hole is a black hole running backward in time, where a black hole's event horizon is a one-way street inward. A white hole's horizon is a one-way street outward. Matter and energy can only erupt from it, and nothing, not even light, can ever cross inside. It is a region of space-time that refuses all entry, a cosmic gusher of pure output. The equations allow for such an object as a valid solution, but the moment you try to imagine how one could form, you run into a wall of paradox. A white hole cannot be created by collapsing matter. That process only makes black holes. Instead, it would have to be a feature of the universe from the very beginning, a singular event where spacetime itself is set to only expel. This leads to one of the most intriguing connections in theoretical cosmology. Some physicists have speculated that the Big Bang itself, the moment of supreme cosmic output, might bear a striking resemblance to a white hole. Our universe's violent beginning, erupting from a singularity of infinite density, could be seen as the ultimate white hole event, a one-time expulsion of all matter and energy from a point of no return. Yet, there is a critical difference. The Big Bang created spacetime itself, while a white hole would exist within an already existing spacetime, making the comparison poetic but not perfect. Another classic role for a white hole is as the other end of an Einstein-Rosen bridge, the theoretical wormhole. In this model, you could fall into a black hole here and, if the tunnel were stable, be spewed out of a white hole somewhere else, perhaps in a distant galaxy or even a different universe entirely. It offers a beautiful symmetry, a complete circuit for cosmic travel. But the white hole's greatest flaw is its profound instability. Think of it like trying to keep a fountain flowing eternally without any source of water. In our universe, filled with matter and radiation, a white hole would be the ultimate target. Any stray particle of dust or photon of light that approached it would be forever stuck just outside its horizon, unable to enter but adding its mass and energy to the gravitational pull. Over time, this accumulating shell of trapped matter would effectively crush the white hole, collapsing it into a black hole almost instantly after it began. Nature, it seems, abhors a one-way exit as much as it might abhor a naked singularity. So if white holes are so unstable, could we ever hope to see one? Some have looked to the most violent, fleeting explosions in the cosmos for clues. When the Swift satellite detected an incredibly bright gamma ray burst in 2006, named JARB 060614, its light curve was bizarre. It had a single, intense spike followed by smaller after-flares, unlike any known supernova or merger. For a brief moment, a few scientists wondered if it could be a white hole, a one-time eruption of energy from a singularity. The idea was quickly overshadowed by more conventional, if still exotic, explanations involving a rare type of supernova. To date, no observation has conclusively pointed to a white hole. They remain phantoms in the equations, beautiful ideas that highlight the strange symmetries of Einstein's universe, but seem to be forbidden by its messy, material reality. They challenge us to ask if every possible mathematical solution has a physical counterpart, or if the universe, in its practical wisdom, simply vetoes certain forms of wonder. White holes remain a mathematical ghost, but the crushing reality of black holes forces us to confront a deeper, universal limit. Every black hole's singularity represents a place where density becomes infinite, a concept that physics cannot accept. This pushes us toward a staggering cosmic question. Is there a maximum possible density in our universe? Could the very fabric of reality have a built-in ceiling, a point where matter simply cannot be packed any tighter? This is not just about black holes. It is about the fundamental rules of existence. The leading candidate for this ultimate boundary is the Planck density. This is not a density we can ever hope to create or measure directly. It is a theoretical extreme derived from nature's most basic constants. To understand it, think of the smallest possible length, the Planck length, which is about 1 trillion times smaller than an atom. Now, imagine packing the entire mass of the observable universe into a cube whose sides are that unimaginably tiny length. The density inside that cube would be the Planck density. It is a number so vast it defies comprehension, roughly 5.1 times 10 to the 96 kilograms per cubic meter. At this scale, the smooth, continuous spacetime described by Einstein's general relativity shatters. Quantum fluctuations of gravity itself would become so violent that space and time would lose all meaning, dissolving into a seething, chaotic foam. This is the realm where a true theory of quantum gravity must reign. A black hole's singularity, with its prediction of infinite density, is a glaring signal that our current physics hits a wall long before reaching this Planck frontier. The singularity is not a physical object. It is a mathematical cry for help, a signpost that reads, "Here, your equations fail." So the quest to resolve the singularity is directly linked to discovering this cosmic density limit. If we can successfully describe the black hole's core with a theory of quantum gravity, it will not give us an infinity. Instead, it will likely show a supremely dense but finite state of matter, perhaps a swirling knot of spacetime itself, hovering at or near the Planck density. This would mean that black holes do not create infinities. They simply compress matter to the hardest possible state the universe allows. They become natural laboratories, showing us the ultimate phase of matter. This idea transforms our view of the cosmos. If there is a maximum density, then there might be a maximum possible temperature, a maximum possible curvature of space, and a minimum possible size for anything to exist. The universe would have absolute boundaries, not just in space, but in the very conditions it can produce. Every black hole, then, is a probe sent to that ultimate edge. By studying their shadows, their mergers, and their theoretical hearts, we are not just learning about cosmic monsters. We are mapping the extreme limits of physical law, searching for the line beyond which reality itself is woven from different threads. The universe's ultimate density limit is a boundary for matter, but there is another, more mysterious arrow that points in only one direction: the relentless forward march of time. This brings us to a profound connection between black holes and the very flow of causality itself. Why does time only move forward? The classic answer from thermodynamics points to entropy, the measure of disorder, which always increases in a closed system. A shattered glass does not reassemble, and smoke never flows back into a cigarette. This increase in entropy defines the arrow of time we all experience. Now, enter the black hole, the object with the greatest entropy in the known universe. A single stellar mass black hole contains more entropy than all the stars, planets, and gas in an entire galaxy combined. Its formation is the ultimate act of creating disorder, taking a complex, structured star and crushing it into an object described by just 3 numbers. So, does the creation and evolution of black holes actually drive the cosmic arrow of time? The connection is startlingly deep. Think of the universe just after the Big Bang, a state of incredibly low entropy, highly ordered and uniform. As the cosmos expanded and cooled, gravity began to clump matter together. Stars ignited, lived, and died. And in those deaths, the most massive stars collapsed into black holes, creating massive leaps in entropy. Each black hole formed is a one-way valve for disorder, a permanent step in the universe's journey from order to chaos. They are not just participants in this process, they could be its primary engines. As black holes merge and grow, their event horizon areas increase, and so does their entropy. This growth might be the dominant way the total entropy of the universe increases over cosmological timescales, steadily winding down the cosmic clock. But the link goes even deeper to the nature of information. Entropy is fundamentally about lost information. The number of microscopic ways a messy macroscopic state can be arranged. A black hole's immense entropy, proportional to its horizon area, represents all the hidden information about what fell in. In this view, the arrow of time points in the direction of increasing hidden information. The future is where more and more of the universe's history is locked away inside black holes, inaccessible to the outside. This paints a haunting cosmic portrait. The universe began in a state of low entropy, with all its potential information visible. As time flows forward, gravity sculpts galaxies and forges black holes, which act as cosmic archives, swallowing and encrypting information. The arrow of time may simply be the direction in which the universe forgets, where the past becomes permanently sealed inside dark, gravitational vaults. It suggests that without black holes, without these ultimate creators of entropy, time itself might not have a preferred direction on a cosmic scale. We would be living in a symmetric, timeless soup. So the next time you feel time slipping away, remember, you are not just living in the universe, you are living in its gradient, a slope created by the relentless, hungry growth of darkness, forever archiving the past to make room for an uncertain future. That cosmic archive of entropy grows with every black hole's birth, a process often marked by the most violent explosions in the universe since the Big Bang. These are gamma-ray bursts, flashes of light so intense they can outshine a million galaxies for a few fleeting seconds. For the long-duration bursts, which can last from 2 seconds to several minutes, the source is almost certainly the catastrophic death of a massive, rapidly spinning star. As the star's core collapses, it is thought to forge a newborn black hole or a hypermassive neutron star. But the central mystery is not the collapse itself, It is the engine. How does this stellar death ignite a pair of ultra-relativistic jets that punch through the star at over 99.99% the speed of light, creating the gamma-ray burst we see from across the cosmos? This is the JRB central engine problem, and it remains one of astrophysics' most intense puzzles. The raw ingredients are there: a feeding black hole, a swirling torus of debris from the shattered star, and ferocious rotation. But the exact recipe for turning that gravitational collapse into a pair of focused cosmic blowtorches is unknown. Physicists are debating between two primary power sources, and the truth may involve both. The first candidate is neutrino annihilation. In the hellish environment just outside the newborn black hole, densities and temperatures are so extreme that a flood of neutrinos and antineutrinos is produced. If these particles collide just above the black hole's poles, they could annihilate into electron-positron pairs, depositing a tremendous amount of thermal energy and potentially driving an explosion. It is a fire born from ghostly particles. The second, and perhaps more powerful, candidate is magnetism. The rapidly spinning accretion disk and black hole can generate magnetic fields of almost unimaginable strength, billions of times stronger than in Mara machine. These fields get twisted into a tight coil like a cosmic spring. This magnetic slingshot could then grab plasma from the disk and violently fling it outward along the rotation axis, creating the jet. The challenge is that both mechanisms face huge hurdles in simulations. Neutrino-driven models often struggle to produce jets that are powerful and focused enough. Magnetically driven models require the star to have a surprisingly strong magnetic field to begin with, or a way to amplify a weak field to staggering levels in mere seconds. The real engine might be a hybrid, where neutrinos help loft material off the disk, and then magnetic fields take over to collimate and accelerate it to relativistic speeds. Furthermore, the disk of debris itself might be unstable, subject to violent oscillations that dump huge amounts of energy into the jet in sudden bursts, which could explain the erratic, spiky light curves we observe. Every long gamma-ray burst we detect is a message in a bottle from a star's final millisecond, a coded signal describing the last actions of a central engine we have never seen directly. By decoding its light, we are trying to reverse engineer the most powerful particle accelerator in nature, built in a stellar corpse in the blink of an eye. The universe's most powerful explosions forge black holes from dying stars, but the cosmic ledger of these dark objects has a glaring gap. We have found the small ones, the stellar mass black holes born from supernova, and we have mapped the giants, the supermassive black holes anchoring galaxies. But what about the middle children? This is the mystery of intermediate mass black holes, the missing link in black hole evolution, with masses between 100 and 100,000 times that of our Sun. For years, they were theoretical phantoms, a necessary stepping stone in our models, yet frustratingly absent from our telescopes. If supermassive black holes grew from seeds, those seeds had to be something more substantial than a single dead star. Intermediate mass black holes are the prime suspects, the potential seedlings that ballooned into the cosmic sovereigns we see today. But if they exist, where have they been hiding? Astronomers point their instruments toward two likely nurseries, ancient and dense environments. The first are globular clusters, spherical swarms of hundreds of thousands of ancient stars, bound together in a tight gravitational dance. In these crowded stellar cities, runaway collisions could occur. Stars might merge, building up a massive object that then collapses directly into a black hole of a few hundred solar masses. The second hiding place is the heart of small, faint dwarf galaxies. If every large galaxy has a supermassive black hole, perhaps every dwarf galaxy holds a smaller, intermediate mass counterpart, a dark monarch ruling a modest realm. Finding them, however, is a monumental challenge. A black hole of 1,000 solar masses is not actively feeding on enough gas to shine brightly as a quasar, and it is too small to dramatically sway the motions of an entire galaxy. We must look for subtler clues, the frantic orbiting of just a few stars trapped close to its invisible grip. Recent years have finally delivered tantalizing candidates. One of the most compelling pieces of evidence came from a peculiar flash in a distant galaxy. In 2006, astronomers observed an ultraluminous X-ray source, a spot of radiation shining with the power of millions of suns. The intensity suggested it was not a stellar mass black hole, but something larger, perhaps an intermediate mass black hole in the act of tearing apart and consuming a star. Then, in 2019, the Gravitational Wave Observatory LIGO Virgo detected a signal unlike any other. Dubbed GW190521, it was the merger of two black holes, but the resulting single black hole weighed in at about 140 solar masses. This was squarely in the intermediate mass range, the first direct evidence of such an object's existence, forged in a collision we happen to witness. Even more recently, studies of the motion of stars in a dense cluster near the center of our own Milky Way have hinted at an invisible mass of several thousand suns lurking there. Each candidate is a piece of a cosmic puzzle, suggesting these middleweight black holes are not missing, but merely masters of stealth, waiting in the shadows of crowded star clusters and faint galaxies. Their formation story remains an open question. Are they the stripped-down cores of small galaxies swallowed by larger ones in the ancient past? Or are they the products of a bygone era when the first stars were colossal behemoths, hundreds of times more massive than our Sun, whose deaths left behind equally massive black hole seeds? Unlocking the secret of the intermediate mass black hole is more than just filling a catalog gap. It is about tracing the genealogy of the most powerful objects in the cosmos, understanding how the universe builds its giants from the dark foundations laid in its earliest, most violent chapters. The final, fading vibrations of a newly merged black hole hold a secret language. When LIGO and Virgo detect the collision of two black holes, the signal tells a story in gravitational waves. There is the in-spiral, the accelerating dance as the two objects circle each other. Then the merger, the violent moment they become one. But the story does not end there. What follows is the ring down, a brief, pure tone as the distorted, single black hole settles into its final, smooth shape, shedding its deformations like a struck bell fading to silence. This tone, its frequency and how quickly it fades, is the fingerprint of the final black hole's mass and spin. It is a direct test of general relativity in the most dynamic regime possible, and so far Einstein's theory has passed perfectly. The ring down matches the predictions for a classical black hole with an event horizon, but some physicists listen more closely, straining to hear a faint whisper hidden within that dying tone. They are searching for gravitational wave echoes. The idea is revolutionary. If the event horizon is not the perfect, one-way membrane of classical theory, but has some quantum structure or a slightly reflective property, then some of the gravitational waves produced during the merger could bounce between this quantum surface and the outer curvature of spacetime. Each bounce would produce a delayed, fainter copy of the original ring-down signal, an echo. Hearing such an echo would be like discovering that a bell you thought was solid has a complex interior chamber, changing its sound in subtle ways. It would be direct evidence that black holes are not the simple, bald objects of the no-hair theorem, but have quantum structure at their boundaries. Several teams have claimed tentative detections of echoes in the publicly available LIGO data, but these findings remain hotly debated and are not yet considered conclusive by the wider scientific community. The signals are buried in noise, and distinguishing a true echo from a random statistical fluctuation is extraordinarily difficult. Yet the search continues with fervor because the prize is so immense. A confirmed echo would not just tweak our understanding of black holes, it would shatter it. It would provide the first observational evidence for physics beyond general relativity in the strong gravity regime, offering a direct window into quantum gravity. It could point toward exotic alternatives like wormholes, gravistars, or black holes with quantum hair. Each echo, if real, would be a whisper from the edge of spacetime itself, a message that the horizon is not the end, but a gateway to a deeper, more complex reality we are only beginning to hear. That subtle echo from a quantum horizon would be a whisper of something new, but the roar of a black hole's jets is a thunderclap of raw power. The leading explanation for this cosmic extraction of energy is a brilliant, complex idea known as the Blandford-Zenagic process. It is a mechanism that treats a spinning black hole not as a simple pit, but as a colossal, spinning conductor embedded in a magnetic field, a cosmic dynamo of unimaginable scale. The process begins with the accretion disk, the swirling maelstrom of superheated gas. This ionized plasma is threaded with magnetic fields, which are stretched and amplified by the disk's ferocious rotation. These fields are not passive. They act like lines of immense tension, rooted in the disk but reaching out into the space around the black hole. Now, here is where the magic happens. The black hole's spin drags the very fabric of spacetime around with it, a region called the ergosphere. Within this whirling zone of twisted reality, the magnetic field lines themselves get caught in the drag. They are wound up tighter and tighter, like a spring being coiled. The Blandford-Zenagic process proposes that this twisting creates a powerful electric voltage across the black hole's poles. This voltage is so immense it rips particles from the vacuum of space itself, creating a plasma of electrons and positrons. These charged particles are then accelerated along the twisted magnetic field lines, which act like the rails of a particle accelerator shooting out from the poles. Crucially, the energy to do all of this, to create the voltage and accelerate the plasma to nearly the speed of light, is stolen directly from the black hole's rotation. Every joule of energy that powers a jet that stretches for thousands of light years is a joule of rotational energy drained from the spinning monster at the center. It is the ultimate cosmic heist. Yet, for all its explanatory power, the Blandford-Zenagic process is draped in its own set of profound mysteries. The first is the origin and structure of the magnetic field itself. How does a chaotic, turbulent accretion disk generate a magnetic field that is both incredibly powerful and globally ordered? We are talking about fields trillions of times stronger than Earth's, and they need to be coherent over vast distances to collimate the jet. Is the field generated by dynamo action within the disk, or is it imported from the surrounding galactic medium and then captured and amplified? We simply do not know how nature builds this perfect, invisible infrastructure. Another major puzzle is the loading problem. How exactly is the plasma that carries the current and the energy created and injected into the magnetic field lines near the poles? The process requires a source of charged particles, but the environment right at the event horizon is extreme. Does the plasma come from pair production in the intense radiation fields, or is it somehow siphoned from the inner edge of the accretion disk? Getting this detail wrong in simulations means the jet either never starts or immediately fizzles out. Perhaps the greatest mystery is whether we can see direct, smoking gun evidence of the Blandford-Zinagic process at work. The Event Horizon Telescope image of M87's black hole showed a lopsided ring of light, evidence of a spinning disk, and the presence of a powerful jet. But to confirm the dynamo, we need to see the connection between the magnetic field structure at the very event horizon and the base of the jet. Future observations, perhaps with space-based radio telescopes or next-generation ground arrays, aim to map the magnetic field lines in polarized light, looking for the telltale twist and organization that the process demands. The Blandford-Zinagic process is our best map to a phenomenal cosmic engine, but it is a map with blank spaces labeled here be dragons. Solving its mysteries means understanding how the universe transforms the silent spin of darkness into the most brilliant beacons in the cosmos. The roar of a relativistic jet is powered by a cosmic dynamo, but the black hole itself possesses a far more subtle and profound heat. It is a cold, almost ghostly warmth, a temperature born not from fire, but from the quantum vacuum of space itself. This is the cornerstone of black hole thermodynamics, a field that began with a stunning paradox and has since rewritten our understanding of reality's deepest laws. The story starts with a young physicist named Jacob Bekenstein. In the early 1970s, he made a radical proposal: a black hole must have entropy. Entropy is a measure of disorder or hidden information, and Bekenstein argued that a black hole's entropy is proportional to the area of its event horizon. This was shocking because entropy is a thermodynamic property, and black holes were considered purely gravitational, simple objects. Stephen Hawking famously objected, arguing that if a black hole had entropy, it must also have a temperature, and a hot object must radiate. But a black hole, by definition, cannot radiate, it only absorbs. Hawking set out to prove Bekenstein wrong. Instead, he proved him spectacularly right. By applying quantum mechanics to the curved spacetime around a black hole, Hawking discovered that black holes do indeed radiate. Virtual particle pairs, constantly popping in and out of existence in empty space, can be split by the black hole's fierce gravity. One particle falls in, while the other escapes as real radiation. This Hawking radiation has a temperature, a precise mathematical temperature inversely proportional to the black hole's mass. A stellar mass black hole has a temperature of barely a fraction of a degree above absolute zero, colder than the cosmic microwave background, but a tiny, evaporating black hole would be blisteringly hot. In one calculation, Hawking united gravity, quantum mechanics, and thermodynamics. A black hole is now understood as a thermodynamic object, with defined temperature, entropy, and even an analog of pressure. It obeys laws that perfectly mirror the classic laws of thermodynamics. The first law is conservation of energy. The black hole's mass changes when it absorbs energy or does work by spinning. The second law says total entropy never decreases, and when matter falls into a black hole, the increase in the horizon's area always outweighs the loss of the matter's own entropy. The third law suggests you cannot reduce a black hole's temperature to absolute zero. as this would require an infinite spin or other impossible parameters. The equations fit together with eerie, beautiful precision. Yet this success hides a conceptual abyss. What does it mean for a black hole to have a temperature or entropy? For a normal hot object, like a cup of coffee, temperature arises from the frantic microscopic motion of its trillions of molecules. Its entropy counts the number of ways those molecules can be arranged while still looking like a cup of coffee from the outside. But a black hole, according to classical general relativity, has no microscopic structure. It is empty space, a vacuum, with all its mass crushed into a singular point. How can nothing but curved emptiness have a temperature? How can a vacuum have disorder? The black hole thermodynamics paradox is not a mathematical inconsistency, it is a screaming clue. It tells us that the smooth spacetime of Einstein's theory is an illusion, a macroscopic average of some deeper, quantum reality. The entropy being proportional to the area, not the volume, is the ultimate hint. It suggests that all the information about what is inside the black hole is somehow encoded on its two-dimensional surface, like a hologram. The microscopic degrees of freedom that give rise to its temperature and entropy must live on that boundary. This is the holographic principle in its rawest form, and it points directly to the need for a theory of quantum gravity. The thermodynamics of black holes is not just an analogy, it is a revelation. It shows that gravity, when pushed to its extreme, reveals its inherently statistical and quantum nature. The warmth of a black hole is the warmth of information itself, whispering that the universe, at its most fundamental level, is not made of stuff, but of bits, of data written on the fabric of spacetime. Solving this paradox means discovering what those bits are, and how their quantum dance creates the force we call gravity. But the thermodynamics of a black hole is a story of its boundary, a surface property. To understand the true grip of its gravity, we must look beyond the horizon, to the space where objects still resist the final plunge. This is the fate of orbiting objects, a cosmic dance that becomes a laboratory for the most extreme predictions of Einstein's theory. We often think of orbits as neat, elliptical paths, like Earth around the Sun. But near a black hole, spacetime is so profoundly warped that these simple ellipses break down into something far more complex and beautiful. An object in a close, stable orbit does not simply loop around. Instead, its orbit itself rotates. The point of closest approach, the periastron, slowly shifts around the black hole with each revolution, tracing a rosette pattern in space. This is orbital precession, an effect seen even in our solar system with Mercury, but near a black hole, it becomes a wild, exaggerated whirl. For a supermassive black hole like the one at our galaxy's center, this precession offers a perfect test. By meticulously tracking the paths of stars like S2, which swings breathtakingly close to the invisible monster, astronomers can measure this precession with exquisite precision. Does it match the prediction of general relativity, or does it deviate, hinting at new physics? So far, Einstein is winning, but the orbits hold deeper secrets. The most extreme paths are known as zoom-whirl orbits. Imagine a star or a compact object, like a neutron star, on a highly elongated elliptical orbit. As it approaches the black hole at blistering speed, it doesn't just swing by. In the region of most intense curvature, it can execute multiple, incredibly tight loops around the hole before being flung back out to the far reaches of its orbit. It zooms in, whirls around several times like a ball in a roulette wheel, and then zooms out again. This isn't science fiction, it's a direct prediction of the equations. The number of whirls is exquisitely sensitive to the black hole's mass and spin, and to the very nature of the spacetime geometry. Detecting an object in such an orbit would be like finding a natural probe executing a pre-programmed test of gravity's strongest possible field. But these orbits lie on a knife's edge. The chaotic nature of gravity so close to the event horizon means that tiny differences in the starting conditions, a slight nudge from another passing star, or the emission of a gravitational wave, can dramatically alter the path. A stable zoom-whirl orbit could, over many cycles, become unstable, sending the object spiraling into its doom, or ejecting it from the galactic center entirely. This chaotic instability is itself a feature, not a bug. It tells us about the limits of predictability in an Einsteinian universe. By observing these frenetic final dances, we could learn not only about the black hole, but about the fundamental behavior of matter and energy in a realm where Newton's orderly clockwork gives way to Einstein's dynamic, curving stage. The ultimate fate of an orbiting object, then, is not just a slow spiral or a sudden capture. It is a detailed map, written in motion, of the warped spacetime it travels through. Each whirl, each zoom, is a sentence in a story told by gravity itself, a story we are just beginning to read. The elegant simplicity of a black hole's three-number description is a beautiful idea, but the real universe is rarely so tidy. The no-hair theorem, which states that black holes are defined solely by mass, spin, and electric charge, is a prediction of pure, classical general relativity. It assumes a perfect vacuum and a black hole in total isolation. Yet the cosmos is a messy, dynamic place. Could the violent process of a black hole's birth, or the complex environment it lives in, leave a permanent mark, a subtle kind of cosmic hair? Observational astrophysics is now putting this elegant theorem to a severe test, searching for the faintest signs of extra properties imprinted on these dark objects. The first challenge comes from the black hole's formation. A star does not collapse in perfect spherical silence. It is a chaotic, asymmetric explosion. If the star is spinning rapidly or has strong magnetic fields, could those characteristics leave a lasting imprint on the resulting black hole, beyond just its overall spin? Could there be faint bumps or wrinkles frozen into the fabric of the event horizon itself, a permanent memory of its violent birth? These would be forms of hair, subtle deviations from the perfect smoothness the theorem demands. Furthermore, a black hole is rarely alone. It sits in a galaxy surrounded by matter, magnetic fields, and other stars. If a black hole is born within a powerful external magnetic field, that field could become locked into the spacetime around it, effectively giving the black hole a magnetic hair that persists even if the external source fades. While this might not violate the letter of the theorem in a pure mathematical sense, it blurs the spirit of it, suggesting the black hole's observable properties can be influenced by its history and surroundings in more complex ways. The hunt for this hair is now a major focus of cutting-edge observation. We have two powerful tools to conduct this search: the shadow of a black hole and the ring of gravitational waves from a merger. The Event Horizon Telescope's image of M87's shadow was a first test. A perfectly bald black hole, described only by mass and spin, casts a shadow of a very specific, predictable shape and size. Any bumps or extra fields would distort that shadow in subtle ways, making it slightly asymmetric or changing its diameter. The first image was consistent with a bald black hole, but the precision will only improve. Future telescopes, with more stations and higher frequencies, will map the shadow's outline with exquisite detail, looking for any tiny deviation from the predicted smooth curve. Even more promising is the data from gravitational wave observatories like LIGO and Virgo. When two black holes spiral together and merge, the gravitational waves they emit are a direct probe of their spacetime geometry. The final ring-down signal, the tone of the new black hole as it settles down, is especially sensitive. The frequency and decay rate of this tone are determined by the black hole's mass and spin, if the no-hair theorem holds. But if there is any extra hair, any other property affecting the horizon, it would change the ring down in a detectable way. It would be like listening to a bell. A perfect, smooth bell rings with a pure tone. A bell with a small crack or an uneven thickness produces a more complex sound, with overtones that betray its imperfections. Physicists are now listening intently to the ring down of merged black holes, searching for those extra vibrational tones, those whispers of hidden structure. Finding even the slightest deviation would be a monumental discovery. It would mean that black holes are not the ultimate cosmic simplifiers after all. They could carry scars of their birth, fossils of their environment, a richer history written in the fabric of their horizons. It would force us to revise our understanding of gravity in its most extreme regime and open a new window into the chaotic processes that create these dark giants. The universe may abhor a naked singularity, but it might just love a black hole with a little bit of hair. The intimate connection between a black hole and its host galaxy is a cosmic symbiosis so profound it defies simple cause and effect. Nestled at the center of nearly every large galaxy, a supermassive black hole seems impossibly small compared to its vast stellar home. Yet, observations reveal a startling correlation. The more massive the central black hole, the more massive the galaxy's central bulge of stars. This is not a coincidence. It points to a deep, ongoing conversation, a feedback loop where the galaxy feeds the black hole, and the black hole, in turn, regulates the galaxy's growth and star formation. The question is how this dialogue works across millions of light years, and which partners started the conversation in the first place. The primary messengers in this cosmic exchange are the black hole's powerful outputs, its jets and radiation. When a supermassive black hole feeds voraciously, becoming an active quasar, it doesn't just consume, it erupts. The relativistic jets we discussed earlier act as cosmic blowtorches, plowing into the surrounding galactic gas. This does two things. First, it heats the gas, preventing it from cooling and collapsing to form new stars. Second, it can physically push gas out of the galaxy's center, starving future generations of stars of their fuel. In this way, a ferociously feeding black hole can quench star formation in its own galaxy, putting a cap on how large the galaxy can grow. But there's a counterpoint. The same energy from the black hole can also trigger star formation under the right conditions. When the jets slam into dense clouds of gas, the shock waves can compress those clouds, causing them to collapse and ignite new stars in a brilliant ring around the galactic center. So the black hole plays a dual role, both a destroyer and a creator of stellar nurseries, a galactic heart that can either still the beat of creation or send it racing. This intricate feedback mechanism appears to be a universal rule, a built-in thermostat that prevents galaxies from growing too large too fast. But the mechanics are maddeningly complex. How does the energy from the tiny central engine couple so efficiently to the gargantuan reservoir of galactic gas? We see the effects, but we don't fully understand the wiring of the circuit. This leads to the ultimate chicken and egg puzzle of cosmic evolution. In the early universe, we see fully formed supermassive black holes inside young galaxies at a time when neither should have had time to grow so large. So which came first? Did a massive black hole seed form first, and its gravity then attract the gas that built the galaxy around it? Or did a primordial galaxy collapse first, funneling gas to its center to forge the black hole? The evidence is still coming in, and it suggests a co-evolution, a simultaneous growth from the very beginning. The first black holes, perhaps from direct collapse or massive primordial seeds, may have acted as anchors. Their gravity helped draw in the first waves of gas, accelerating the birth of the first stars and the proto-galaxy. As the galaxy grew, it fed the black hole, which then began its feedback, regulating the feast. They grew up together, locked in a gravitational embrace, each setting limits on the other's destiny. This means the black hole at the center of a galaxy is not a passive occupant. It is an active architect. Its past outbursts, visible as faint radio lobes stretching far beyond the visible stars, are fossils of its earlier influence, showing how it shaped the galactic ecosystem over billions of years. The quiet black hole in our own Milky Way, Sagittarius A star, likely had such active phases in the distant past, its jets sculpting the very structure we see today. Solving this co-evolution mystery is about understanding the life cycle of galaxies themselves. It asks how something so small can wield such large-scale power, and how the universe orchestrated a delicate dance between darkness and light to build the majestic islands of stars we call home. The black hole's core is a place where our familiar rules of space and time dissolve. But perhaps this dissolution is not an end, but an opening. String theory, one of the leading candidates for a theory of quantum gravity, paints a picture of a universe with more than just the three spatial dimensions we experience. It suggests there could be 6 or 7 extra dimensions, curled up at scales a billion times smaller than an atom. In our everyday world, these dimensions are invisible, compactified into a shape we cannot perceive. Yet at the heart of a black hole, where gravity becomes infinite and spacetime curvature runs wild, something extraordinary might happen. The singularity could be the point where these tiny, hidden dimensions unfurl. Imagine the crushing core not as a point of infinite density, but as a knot where our three-dimensional space unravels, revealing a gateway into a higher dimensional geometry. In this view, the matter falling into a black hole isn't crushed into nothingness. It is funneled into these extra dimensions. The infinite density predicted by general relativity would simply be an artifact of our incomplete, three-dimensional perspective. From a higher dimensional viewpoint, the mass might be smoothly distributed, resolving the mathematical catastrophe at a stroke. This is a radical reimagining of the black hole's heart. Instead of a dead end, the singularity becomes a cosmic subway station, where the tracks leading out of our universe are dimensions we cannot normally access. What would this look like from the outside, or could we ever detect it? The signatures would be subtle, woven into the fabric of the black hole itself. One possibility lies in the way black holes evaporate via Hawking radiation. If extra dimensions are accessible at the singularity, they could alter the types and rates of particles radiated away. We might see an excess of certain high-energy particles, or a specific pattern in the radiation spectrum that defies the standard model. Another clue could be hidden in the gravitational waves from merging black holes. The ring-down phase, the final tone as the new black hole settles, would carry the imprint of its structure. If the core interacts with extra dimensions, the vibrational modes of the merged black hole could be different, producing faint overtones in the gravitational wave signal that our current detectors cannot yet hear, but future observatories might capture. There is also the shadow of a black hole. The precise shape of that dark silhouette against its glowing ring is exquisitely sensitive to the space-time geometry right at the event horizon. If that geometry is influenced by higher dimensional physics lurking just beneath, the shadow might show a minute telltale distortion. While these ideas remain at the very frontier of theoretical physics, they transform the singularity from a wall into a door. It suggests that the ultimate breakdown of our laws is not a failure, but an invitation to step into a broader reality, where the universe is far richer and more interconnected than our senses have ever allowed us to see. The preservation of information is a physical law, but the survival of a self is a different kind of mystery altogether. Our final question ventures into this profound and unsettling territory. If all the quantum information that describes an object is, in principle, encoded on the event horizon and eventually released in Hawking radiation, then what about the most complex information structure we know, a conscious mind? Could the precise arrangement of atoms, the electrical patterns of thought and memory that constitute a person, ever be reconstructed from that scrambled, thermalized data? This is not a question of engineering, but of philosophy and physics colliding at the edge of a singularity. The modern view leaning toward information preservation offers a chillingly technical possibility. Imagine an astronaut, a person with a lifetime of memories and experiences, falling into a very large black hole. According to the holographic principle, all the information that defines that person is imprinted on the horizon. Over the aeons, as the black hole evaporates, that information is slowly, randomly emitted in the Hawking radiation. In a universe with a godlike physicist and an infinite amount of time, one could, in theory, collect every single emitted particle and reverse engineer the evaporation. Through calculations of unimaginable complexity, one could reconstruct the complete quantum state of everything that ever fell in, including the astronaut. From that state, you could, again in principle, reassemble the person atom by atom, synapse by synapse. The data would all be there, but here, physics runs headlong into the problem of identity. The reconstructed person would have all the same memories, the same sense of self, the same conviction that they had just fallen into a black hole. To them, it would feel as if they had simply passed through a chaotic tunnel and emerged elsewhere. Yet, from the outside perspective of the universe they left behind, they were vaporized into fundamental particles billions of years ago. So, who is the real person? Is it the pattern of information itself, which has now been reinstantiated? This is a cosmic-scale version of the classic teleportation paradox. If your body is scanned, destroyed, and an exact copy is assembled light years away, is that copy you? Most interpretations say no, it is a perfect replica, but the original stream of consciousness ended. The black hole scenario is even more extreme because the information is not just transmitted, it is horrifically scrambled and hidden for eons. The reconstructed being would be a distant, separated copy, not a continuous self. This forces us to ask what we truly are. Are we the physical stuff, the specific atoms arranged in a specific way at this specific moment? If so, then the astronaut is gone forever, their atoms crushed and their pattern dissolved into the vacuum. Or are we the abstract pattern, the song that can be sung by different instruments? If consciousness is substrate-independent information, then perhaps the pattern's reappearance, however delayed, is a form of survival. The black hole becomes the ultimate test of this idea. It suggests that in a universe governed by quantum mechanics and information theory, death by singularity may not be an absolute erasure, but a transformation so radical it lies beyond our current understanding of life, continuity, and time. It hints that the universe might be less concerned with preserving the vessel and more with preserving the message. The final mystery, then, is not just about the fate of matter, but about the nature of existence itself. In the silent darkness of a black hole's heart, we are left to wonder if the cosmos remembers who we are, long after every star we knew has faded to black. From the preservation of a single consciousness to the birth of entire universes, these 30 mysteries are more than a catalog of cosmic curiosities. They form a single, sprawling map of our ignorance, a testament to how black holes have become the ultimate laboratories for physics. Each one is a paradox, a place where our most trusted theories clash and shatter, forcing us to invent new ways of seeing reality. They are not mere vacuum cleaners in the void, but active, dynamic engines that shape galaxies, forge the elements of life, and challenge the very concepts of space and time. Every unanswered question, from the firewall paradox to the whisper of gravitational wave echoes, is not a dead end. It is a doorway. Stepping through it requires us to rewrite the rulebook of the universe, to glimpse a deeper layer of existence where information is the true currency and gravity is a language we are only beginning to decipher. This journey reveals that the greatest darkness in the cosmos holds the brightest promise for discovery. So tell us, which of these mind-bending mysteries keeps you awake at night? Is it the terrifying possibility of a naked singularity, the holographic nature of reality, or the haunting question of what truly happens at the point of infinite density? Let us know in the comments below. And if this exploration into the unknown has sparked your curiosity, be sure to like this video and subscribe for more journeys to the edge of understanding. The universe's greatest puzzles are waiting, and the next revelation is always just one